My name is Pavel Hubacek. I'm a cryptographer. I currently work at the Czech Academy of Sciences and teach at Charles University. And like in my research, I spent the past few years thinking about these verifiable delay functions and this particular part of theoretical cryptography. And I think that these things are very cool. People should know about it. I guess the average member of the audience here should be able to build something cool on top of it. So I would love to tell you about this. Related to that, I would love if you ask questions during the talk, right? If there's something that you don't understand, possibly it's my fault, right? Like I'm not explaining myself clearly, so just shout. And I might not see hands that are raised, so just shout and ask and make sure that I don't run too fast. I try to not make it very technical. So what are the cryptographic foundations of blockchain? Well, you know very well the proof of work, right? So the proof of work is this thing that allows someone to prove that they spend some amount of work, right? And it is great. It comes from way back when people started first thinking how to avoid spam attacks and how to build CAPTCHAs, how to even define CAPTCHAs, right? And the issue with this is that, well, it works very well, but has a lot of downsides, right? Like you need to spend a lot of energy on computing the proof of work. Then there is this issue of parallelizability, right? You have this computation where if you have more CPUs, more cores, you compute faster, and that's not what you want, because then it leads to special purpose hardware. People use GPUs, then people use ASICs, and suddenly, the system that came with the premise of being decentralized, is split into these groups of super miners, and they have a lot of power over the system. You would want to avoid that. And very fast, people realized this and started proposing alternatives, right, to this proof of work, something that's different. Well, one of the first things that came up was proof of space or storage. So the idea is that, well, instead of spending computational power, I could use proof that I allocated some empty space. I put it on the side. I'm not using it for anything else besides, the consensus, right? This is motivated by this very hand-wavy argument that it's more difficult to buy more space than buying special purpose mining hardware. But once you go this way, you very fast realize that there is issue in defining this notion, this proof of space or proof of storage, and that is that what does it mean to prove that I have allocated some space? Does it mean that when I was proving I had the space, or does it mean that from time t to time t plus 10 minutes, I had this space aside, right? So this motivated the refinement of proof of space, which was proof of space-time, which is closer to what you would expect, right? Like that you had this space aside for some specific time. And it's used in some blockchains. I think that last time I looked, there was this mesh cache, space mesh. So they wanted to use something like this. Then not going towards space, but trying to work with the issue of parallelizability are these proofs of sequential work. So this is a different direction where you say, well, okay, so if parallelization is the issue, then let's not build our proof of work around computation that is highly parallelizable, but let's design computation where you need to actually work sequentially. More processors are not going to give you advantage. And this sounds reasonable. It's a way how to fight GPUs, how to fight ASICs, right? So these proofs of sequential work they are very cool, like as mathematical objects. Like the constructions that people developed, they use very exciting like mathematical results from combinatorics, and yet they are like somewhat practical because they are based only on hash functions. So it's like very nice. But today, I want to talk about like the next iteration of this line of progression in the world of cryptographic puzzles, and those are verifiable delay functions. Right? So delay functions, there is this cute sloth, something that takes long time to compute, that like is slow. And verifiable delay functions, the main difference compared to, let's say, proofs of sequential work or the previous things, that they are like functions. Like the puzzles, like the proof of work puzzle that we all know, right? That has many possible solutions. We just need to find a preimage that specifies some constraint. But there are many preimages like this, and it's used in order to tweak the hardness of the puzzle. In verifiable delay functions, the solution is unique. And this is great when you try to build something on top of it. That's why verifiable delay functions are very useful directly for applications, because they have this uniqueness property. They're like slow to compute, but once you have the solution, that you are guaranteed that it is unique. And we'll talk about it in a moment when we discuss some applications. So I have to go way back to introduce you to some background. So all of this, like problems that are like hard to compute sequentially, they go way back. Well, like this is kind of a real life motivation for like the sequential computational problems that are sequentially hard. So in 1951 at MIT, they had this great idea. Let's send a secret message to the future. And that's kind of what we want to do when we design many of these cryptographic protocols on blockchain. We want to send secret messages to future that will stay secret until it's the time to reveal them, and then we will work with them. So what they did, I think it was the physicists, they created this amazing vacuum tube that they put into all this information about the era and like some greetings to the future, and they wanted this to stay sealed for a millennium. Right? So they said that this shouldn't be opened until 2950, whatever, 1 or 7, I guess. So what happened, right? MIT is a good school, so they have a lot of funding. They keep on building in the campus, and during one of these, construction works at the campus, they found the vacuum tube, and it was written, "Please do not open until 2957." Yet, what do you expect? They opened it, right? So we cannot rely on trusting people to not open our time capsules, right? So that's the scary revelation. We cannot trust people. How do we solve this issue? Then, well, we need to use cryptography, right? So here is an approach, like a template, or call it a recipe, how to build these time capsules. And this is use some like inherently sequential computation, right? In real life, like the physical world, we have such processes that are inherently sequential, right? So here is an example. If I put cake into the oven, it takes, depending on the recipe, let's say 40 minutes to bake it. Now, can I speed up the process? If I have access to 2 ovens, can I bake the cake faster? I don't think so. Like, you shouldn't try. So here is the idea, right? Like we're gonna send a secret message to the future just by using some inherently sequential computation. However, we need to have this property, like we want to, let's say, encrypt a message, right? So when I'm creating this puzzle that has some prescribed time to solve, I need to also have a solution, right? So that using the solution, I can encrypt the secret message that I'm sending to the future. So these are the 2 properties of these computational problems, and like they are not very common. It's like one of the sad truths of my talk. Like we don't have many good sources of sequential hardness that we could work with. And it's one of the open problems that I'll mention at the end. So how did people, like solve this problem? Well, there was Rivest, Shamir, and Wagner. So Rivest and Shamir, they are, behind RSA. Wagner, I think, was a student at that time at MIT. So they wrote this report where they described how to build something that they call a time lock puzzle, a cryptographic time lock puzzle. This is exactly the time capsule functionality. Okay. So what is the inherently sequential computation? And this is like the canonical one. When people think about inherently sequential computation, oftentimes they think about this. So it's just taking some like iterated squaring over some RSA modulus. So, here is, if you're getting lost, just shout. I will try to explain better. So basically, the input is x, t, and n. N is the modulus. So we're computing modulo n. And what we want to compute is x to the 2 to the t. Okay, so we're raising x to the 2 to the tth power. Okay, so if t was 1, it would be just squaring, right? And this is somehow like the iterated squaring. And it's very natural to think about it as iterated squaring because, right, like how many steps do you need in order to compute this x to the 2 to the t? Well, that's t, right? And what do I mean by a step? A modular multiplication, right? Why t? Well, like this is something that like basic algorithms course covers, right? We have this square and multiply approach to doing this, exponentiation. So basically, you compute the first square, so you have x squared. You can multiply x squared with x squared. You're getting like x to the 4th power. You get x to the 4th power times x to the 4th power. You get x to the 16th power. So basically, you go and in t steps instead of 2 to the t steps, right? But in t steps, you get to where you're supposed to be, right? And now, we can set t as much as we want. And we can estimate how long does it take on a CPU. And here is an assumption, and it's the assumption of RSW, that this is actually the best way how to compute this result. So you cannot do much better than just doing the iterated exponentiation. So t steps is the best. The truth is, it's like not completely correct. There is a very smart algorithm by Bernstein and Sørensen that slightly improves this. So if I give you some parallelism, it helps a bit, but not much. So, like it takes almost t steps, and this is the assumption that people take, that, like it is like reasonably robust up to the algorithm of Bernstein and Sørensen. So, okay, this is the process, right? The question is, can we do it much faster if we have, let's say, FPGAs or some, like something that has many cores, and we're believing not. And how do we build a time capsule out of this? Well, okay, so here we're getting to generating a problem together with a solution, right? So it's easy to generate this problem. Just pick a random x and say, this is the problem, x, the time parameter, and the modulus. The solution then is y that equals x to the 2 to the t. And if I have a message, that has 2048 bits, then I can, encode it as an element of the corresponding group and just add it modulo n. It's like, like taking your message and one-time padding it with this hard-to-compute thing. And this is, my time capsule. So I'm basically just taking the message that I want to send, and I'm, like one-time padding it with the hard-to-compute information. Now the thing is that this is not a very good time lock puzzle, because in order to generate it, you need to spend as much time as you need to solve it, right? So this is what we don't want. We want puzzles where generating the solution together with the instance is much faster than solving it. And here, right, this is what RSW observed. They knew it very well, the algebra there. So you can actually solve it much faster. That is, if you know the factorization of the modulus. So, similarly to the RSA problem, right? The RSA encryption, once you know the factorization of the modulus, there's no security, right? You can solve, all of these equations much faster. How do you solve it? Well, it's basically just if I know that n is a product of p and q, then I know how many elements of interest are there, like how many elements of the RSA group there are, and I can use it to, compute exponentiation much faster. I don't have to compute x to the 2 to the t. I can just take 2 to the t and reduce it modulo p minus 1 times q minus 1. This is the number of elements of the RSA group. And we're doing this finite arithmetic, so you know that every p minus 1 times q minus 1 things will wrap around. So you can just erase all of that and just care about the reminders modulo the order of the group. So this is actually something that is much smaller than 2 to the t. Let's say that t is 2 to the 80. And so that's a lot, right? 2 to the 80 is a lot. And this is 2 to the 11, right? So now I have r, which is like much smaller than 2 to the 2 to the t, right? So, I can solve just by this very efficient exponentiation modulo n. So this is how I set it up. And I publish. What do I publish? I publish C. That's the time capsule. I publish x, t, and n so that you know how to get to the thing that will unmask the message and let you compute. The only thing that I need to do correctly is to estimate how much time does it actually take to do this modular repeated exponentiation. And that's non-trivial. So let's get to the real time capsule. So in 1999, Ron Rivest created a time capsule that was supposed to be for the celebration of the 35th anniversary of the CSAIL lab at MIT. So CSAIL is the computer science and AI lab, like the people that do crypto and theory at MIT. They were celebrating 35 years, and they thought, let's make a time capsule, right? One where we don't have to pretty please people to not open it, right? So let's do it cryptographically. So Ron Rivest sat down and did it, and this was, you could go on his website and see how the time capsule was generated. So n is the product of two primes. He didn't tell which primes, right? And then t is the time parameter, and z is what I called c, the time capsule. And if you would compute, so he set it up that x was 2, so if you would compute 2 to the 2 to the t mod this n, then you should get the w such that when you sum w and z, it releases the secret information in this time capsule. And Ron sat down and he said, well, this should take 35 years to solve. We're celebrating the 35th anniversary of CSAIL, so let's give you a puzzle that you will open at the 70th anniversary. And the progress on solving this kind of problems was faster. So there is a QR code. If you are interested, you can go and see a presentation of Ron Rivest that tells the story how this problem was solved. But basically, like 20 years after publishing the puzzle, two teams, like a day apart, they solved it. There was a very smart programmer that wrote a very cool piece of computer program, and in, I guess, 3 years of computing time, he solved it, he submitted it, and the day after, a team of researchers that did some other hardware optimizations for this modular arithmetic, they also solved it, and they came in second, and they had a great party at MIT, right, opening this puzzle. And Ron Rivest published a new one. So that's the CSAIL 2019 puzzle. If you want to think about breaking this sequential hardness assumptions, I think that this is a cool one because like if you solve it, you get to interact with very cool people. So that's the status of sequential hardness up to some point. So that's what we have. We have these time lock puzzles. We are able to generate a hard problem to solve together with a solution. But the issue, right, is that you need to be Ron-Rivest. In order to generate a solution, you need to know the factorization of the n, and that's what we don't want in the wild. Like in the wild, and it will be important for the verifiable delay functions, we want to be able to generate these hard problems without private information. So let's be more specific. So verifiable delay functions, what are they, right? So verifiable delay functions have these three nice properties. One is efficient sampling. Like this, you will create an instance, right? And then it is a delay function that is important. It takes some prescribed wall time, like how to for it to solve. And there's non-trivial, engineering into, estimating this. You need to have like the best implementation on the planet to understand how to set the timing, right? So like there's a lot of research that like has been done and could be done in there. And the nice thing is that it has unique output. And this is the good thing for applications. So the solution is uniquely determined, right? For the time lock puzzle of RSW, it was the case, right? It was a result of this modular equality, and it is efficiently verifiable. And this is new. Okay, this is different from time lock puzzles. It should be efficiently verifiable for everyone. So now, the time lock puzzle, right? Somebody comes and says, well, I computed x to the 2 to the t. It's y. Now, how do I trust this person? How do I verify it, right? Unless I'm the one who set up the problem, right? Then I have the factoring and I'm able to do this. But it's completely unclear how can we, publish these mathematical problems such that after one solves it, he also is left with some succinct proof that anyone can verify without the knowledge of the private information that's possibly there. So that's the efficient verification. That's why there's a unicorn. Not just that it's unique, but it's something very hard to obtain. So why, right? So delay function. How do you build a delay function? Like any one of you, if you think for 5 minutes, you will come up with a delay function, right? What is your delay function? You're going to take a hash function and iterate it t steps. Hash function is very random, right? And there's not much that you can do to parallelize t times iterated hash function, right? This is the most natural thing that you could design in order to build a sequentially hard function. But this is very hard to verify unless you have some very cool crypto like snarks and starks. But a priori, it's not clear that there's some very nice, elegant way to verify the output of t times iterated hashing, right? So getting a delay function, that's easy, but to get getting it together with the efficient verifiability property for everyone, that's hard. Or getting the efficient verifiability property for everyone is easy, right? Just take your function to be identity. On x, I return x. It's very easy to verify, but has no sequential hardness, right? So really, the big question that was open and the people were waiting for this very anxiously was how do you get both in some nice way? And around 2018, there were constructions. So, okay, so what was I saying? Well, we have these constructions, it's like iterated hashing and snarks. That's something that, I guess Starkware did at some point, and like some candidates for this, for Ethereum VDF are based around this. And then there are these elegant, like more mathematical approaches that use iterated squaring, the RSW puzzle, together with proof of exponentiation, like a way how a person that doesn't know the factoring of n can, together with the solution, also give a very short proof that will be convincing to anyone, again, that doesn't have the factorization of the modulus. So here is a construction of verifiable delay function by Veselovsky. So Benjamin Veselovsky worked a lot on sequential hardness, and eventually he came up with this like amazing like a one-liner proof of correct exponentiation. So there's a prover that is trying to convince a verifier that y equals x to the 2 to the t modulo an RSA modulus. So he did the work, and now the verifier will do the following. So the verifier will just sample a random prime L that has lambda bits. So, like lambda is our parameter. Depending on how big is the lambda, that will affect the security of the proof. So it will just sample a random prime of lambda bits and send it over to the verifier, to the prover. Sorry. So the prover then will compute the proof as somehow like a partial exponentiation. Okay. So the prover originally computed x to the 2 to the t. Now it will compute x to the 2 to the t over L. So we take this huge modulus, right? This huge exponent, we reduce it modulo the prime, right? And take the ceiling of this. So this is the S to which we raise it and send it over to the verifier. And now the verifier can efficiently use this in order to compute, right? To check the veracity of the statement. So the verifier can take the proof, raise it to the nth power. So this will give you basically, I suppose, the ceiling, the floor of 2 to the t over L, right? So he raises it to L, and this is almost x to the 2 to the t, except for some remainder modulo L, right, of 2 to the t. So it just computes the proof to the L times x to the remainder. If you do the algebra, you will see that this actually, if everything was correct, is equivalent to x to the 2 to the t. And here the verifier is doing very small exponentiations, right? So R is a remainder modulo L, so it has at most lambda bits, so it's small. L is lambda bit prime, so it's also small. So it's much faster than recomputing the thing itself, right? And if everything went fine, then it will see, the verifier will see that y equals the product of these. It will be happy. And now, why does it prove anything? Well, if you assume that, computing random, so if I give you as a challenge random prime and ask you to compute a random nth root of a random element is hard, then it is secure. So basically, Veselovsky came up with this new computational hardness assumption that, basically, it's like almost equivalent to saying that the protocol is secure, but it's somehow meaningful. And under this assumption, he built, verifiable delay function, right? So what does this do? The prover doesn't need to know the factorization of the modulus, right? What does it do? Computes the pi is x to some power, right? Which is based on this random element from the verifier. So it does basically what it was supposed to do, right? So you can think about it as it kind of solves the problem twice. Yet, after this, it will have a pi that will make the verifier accept the veracity of the statement, right? So it's very cool. So, just twice the amount of work, and you are equipped with a proof that, you constructed without knowing the factorization, and the verifier can verify without knowing the factorization. And, right, so, as a, maximalist, you wouldn't want to interact with the verifier. And there's a common trick, because L is just a random prime, so the verifier just tosses some random coins. So we don't even need the verifier. The prover can just hash, let's say, y and x and t and n, and derive the prime out of this, and then use it to compute. And this is actually going to be secure. It's known as the Fiat-Shamir transformation. It's like a very standard way how to get such a protocol that is interactive, but the verifier just tosses random coins into something that is non-interactive. So here you have very minimal and beautiful proof, right? So proof of correct exponentiation. So if your delay function is this iterated squaring, then you have also the verifiability property, right? So it's amazing. And the proof is minimal, right? So I give you y, x, t, and n. And on top of this, I give you one more element of the RSA group, right? So it cannot get much better than this. However, the security is only computational, and you have to have this new hardness assumption that, I don't know, might not hold, right? Like it's not studied. It was introduced in the context of this protocol, so maybe someone will find a smart way how to break it. But for now, we don't see any reason why it shouldn't hold. Okay, so that's Veselovsky. Now, around the same time, it's amazing, Krzysztof Pietrzak from IST Austria came up with an alternative proposal for doing exactly the same thing, to do public verifiability of the RSW delay function. And he used some ideas that go to the foundations of interactive proof systems. So his approach is, we're supposed to verify the statement y equals x to the 2 to the t, right? So this is what we're supposed to verify, and the verifier cannot do it efficiently, right? Recomputing this takes t steps, and the verifier should be much more efficient than that. But there is a way how to take this statement and, via an interaction with the verifier, reduce it to a much smaller statement that the verifier can check efficiently. It's a statement of a form that some different y equals just x squared. This is something that the verifier can compute very efficiently. And the property of this process is that if this didn't hold, then the statement that we derived with overwhelming probability is not going to hold. So we take this very long computation and then gradually fold it to a very short computation where, if the prover lied, then we're gonna catch him, right? Because we can check the small statement efficiently. It's a very generic approach of building these interactive proof systems. Again, so, okay, we need log t rounds of interaction, but log t is much smaller than t, right? If t is 2 to the 80, right, then log t is going to be 80. It's okay, maybe you can play with the parameters to get something that is better for your application. And one interesting aspect is that the security of the protocol in Pietrzak's case is much stronger. It's something that actually, I worked with some co-authors and Krzysztof. So the protocol has so-called statistical security. Okay, this is something that even cryptographers sometimes don't distinguish. And the thing is that is security can hold against computationally bounded adversaries. This is what we usually do. RSA is secure if you cannot factor, right? So if I give you enough computational power, you can factor the modulus, and security is out of the window. But we can ask for something stronger, and that's statistical security. And this basically says that the setup of my system is so that the probability of being able to cheat just over the randomness of the setup is negligible, and therefore even if I have computationally unbounded adversaries, in majority, like for majority of the setups, they will not be able to do anything, right? So, and this is great because these verifiable delay functions have two properties. One is the sequentiality. Sequentiality we're getting in this context from the iterated squaring. And there we need to assume the computational limitations of the adversaries, because if the adversary could factor the modulus, they could simply compute much faster. But we also have this security of the proofs, right? Somebody comes and proves to me that the result of the computation is correct. And in case of the Pietrzak's proof, you actually know that even if the adversary is computationally unbounded, it's not going to be able to convince you of wrong statements. And this is great, like if you have a system where your proofs are like long living. Maybe tomorrow we will wake up and there will be much better algorithm for this iterated squaring, and therefore we will not have the sequentiality of the iterated modular squaring. Okay, so we'll need to find a different delay function, but still it doesn't jeopardize the security of the proofs. So like all the proofs that we had and anyone would attempt to do are going to be valid, and that's going to be true even if the sequentiality is out of the window. It's very nice, and for some applications it's actually very important. So what we did eventually, sometime after Pietrzak's proof, with Charlotte Hoffmann, Karen Klein, Chetan Kamat, and Krzysztof Pietrzak, we showed that you can get this statistical soundness property for arbitrary group where you compute this modular squaring. In the original proposal of Pietrzak, it held only for like very special type of groups, and it was limiting the kind of setup and also the applicability of the protocol. So we have some nice results about this. What I want to mention is that there is this amazing property of these VDFs, or these proofs of exponentiation, and that is you get batching in a very natural way, the best way that you could think of, kind of for free. So let's say that I have many statements, right? And this is likely going to happen. I mean, for those of you that know zero knowledge and you've seen these polynomial commitments, you know that you might have to commit to many things, and then you would like to do some batching, and batching is good in general, right? So here we have k statements, and we want to verify them much faster than what it would take to do the k verifications, like proving, right, and verifying much faster than k. For these proofs of exponentiation, you can just do the following trick. So you take all the statements and cross-multiply them in some consistent way. So you pick random exponents alpha. So there are k exponents. You have k of the statements. You take k exponents. And then instead of k y's, you will create a single y. The single y is the product of all the y's, but raised to the exponents. So you take the y's, each raised to its corresponding alpha, and then you cross multiply. This is going to give you a new y. Then you take all the x's, right, and do the same. You just raise each x to the same alpha for the I, and then cross multiply. You compute the product, and now the new statement, right, just by algebra, is that the cross product of y's raised to these alphas should be equal to the cross product of the x's raised to the alphas to the 2 to the t, if it held for the k instances. So instead of giving you k proofs, I can give you the alphas, right, or derive them somewhere, and then prove to you that this statement is true. And Lior Rotem had a paper recently in the TCC conference where he showed that this is a sensible thing to do, and depending on the size of these alphas, you get the security bound, and again, like there is some assumption that you need to live with, but that one is much better than, hopefully, than the Veselovsky assumption that I mentioned from the last slide. And that's why these proofs of exponentiation and the PDFs based on proof of exponentiation are so cool. Like, there's a lot of algebra. On one hand, it might mean that none of this has the security properties. So, like, the more structured your problem, the more likely you are to solve it, right? But like, for now, we don't know how to solve it. So let's try to get the most out of it. So because of the algebraic nature of the problem, for example, batching comes for free. And that's not true if you would go back to the iterated hashing plus snark approach. So there, you need to work harder and don't get something like this out of the box, right? Or you might be able to do it, but it's much less elegant than this. So okay, this is like the moment of Zen. What I want to tell you about, and I don't have much time. Can I take like 5 minutes? Is okay?
Yeah, man, you got plenty of time.
Okay. So I want to tell you about recent work that made me very happy. So a student of mine, Tomáš Krňák, for his master's thesis, was looking into this very intensely, and in the end, we managed to generalize a bit this hardness of these RSW puzzles. So what I told you is, we don't know where are these sequentially hard functions. Iterated hashing or this iterated squaring, those are the main sources of sequential hardness. And there are some very strange proposals. Now we have some new kind of proposal that should be post-quantum secure. But in general, we don't know where to get them. And here is one approach how to kind of go above the RSW puzzle. So don't worry. There's nothing horrible happening on the slide. So you saw the picture about the golden ratio. Why did I put it there? There are these Fibonacci sequences that you possibly heard of, right? The rabbits of Fibonacci. Fibonacci sequences are just some recursive linear sequences, and if you write them in a very general form, what you get are so-called Lucas sequences. So here are some recursive sequences. They are parameterized by some p and q, those are just integers. And to compute the sequence u or v, you do it according to this rule. So you just, to compute the ith term, you take p times u I minus 1 minus q times u I minus 2. So you take a look at the previous two terms of the sequence, do this linear combination of them and get the ith one, right? In order to define the sequence, I have to tell you where to start. So you start with 1 and 0, and from that moment on, you can compute the sequence u. The same for v, right? There is some sequence. And what is interesting about these sequences is that, and people observe this, cryptographers notice this, they behave very much like this iterated modular squaring. So people use these modular Lucas sequences to define analogs of RSA and LGAML encryption, hoping that maybe they're going to be more secure than RSA and LGAML encryption. It turned out not to be the case, but nevertheless, they are there, and they've been studied like crazy. Very smart people looked into these sequences and proved very interesting identities that might be useful for applications. So this is the one thing. So here I'm going to give you a candidate delay function, right? So instead of iterated modular squaring, just do iterated computation of these modular Lucas sequences. So I have these sequences, u and v. So I give you the setup. I give you p, q that define the sequences. I give you the time parameter and the modulus. So compute the 2 to the teeth term of the sequence u and v modulo n. Okay. Now, one of the identities that if you would go to an old textbook about these Lucas sequences is that basically you can do analog of square and multiply, right, to compute this in t steps. And what we proved is that this computing the t step is at least for the modular Lucas sequences is at least as hard as the RSW sequentiality problem. So what we have here, to me as a cryptographer, it makes me jump meter high. I want to convey the message to you. So we have a sequentiality hardness problem that might be sequentially hard, even if you give me tomorrow an algorithm for the RSW puzzle, which is great. This is like how I want to work as a cryptographer. I want to, have these verifiable delay functions and be able to build them from various hardness assumptions, because, smart people will try to break my problems and they might succeed. So the more I have candidate problems, the higher the likelihood that at least for one of them, I still have a secure instantiation of the object that I'm building. So here is what Tomáš managed to prove about Lucas sequences. And you could ask, okay, so, it's at least as hard, so how about the other way? So the other way, like showing that, if you can break the RSW sequentiality, then you can break the sequentiality of this Lucas sequences, is not at all obvious. I think that, maybe some smart mathematician could solve it, but we don't see a way how to do it, at least for now. And for us, it's an interesting thing to have a new candidate for sequential hardness. And because you have these parameters P and Q, it allows you more freedom. Might be interesting if you're actually trying to optimize your hardware or something for the VDF. And okay, so this is just the sequentiality part. And then what I want to say about the verifiability, well, if you work somewhat hard, not extremely hard, then you can actually realize that the Pietrak's proof of exponentiation can be applied to these modular sequences. So we also get the verifiability property, not in a new way. So that is a bit of a downside. We reuse the current technology, but well, in the end, we get a new candidate VDF. So that's about the modular Lucas sequences. Just quickly, let's go over some applications of these VDFs, right? So VDFs, X, I'm computing f of X. It takes prescribed time to find the result, right? So you can think about the result as being random, right? So we have a person that's trying to play a lottery, right? We pick X at random and make the person put money, to bet on this X, put transaction into some smart contract, right? Whatnot. And then we will not know until the prescribed time t, at which point we will all know the solution and we can tell whether the person won or lost, right? So this is exactly how you get this, what you get for free out of these verifiable delay functions. Now, basically, the underlying thing that you're getting here is some kind of a randomness beacon. So there are various protocols that build decentralized randomness beacons based on these verifiable delay functions. And there are also some proposals, right, how to use a VDF together, let's say, with a proof of stake, right, to get more efficient, and I'm talking about, energy efficient consensus, right? So I think that now there was even some patent application of Dan Bonnet, Krzysztof Pietrak, and their co-authors that is proposing exactly this, get a consensus mechanism out of proof of stake and the VDF. And already before VDFs, you would be able to do sealed bit auctions just from time lock puzzles, right? If we don't care about this public verifiability, we're fine with revealing the secret information. So time lock puzzle allows me to send a secret message to the future, right? What do I do when I'm participating in an auction? I take my bit, I put it into the time lock puzzle, set the time period for the bidding period, right? Everybody submits their bids. After the bidding phase is over, we take the time to solve the time lock puzzles, then we will learn everybody's bids, and we decide on who is the winner of the auction. So that's something that we knew, and you can get it. You can build, for example, a sealed bit auction just out of this time puzzles in cryptography. An interesting thing that happened very recently, and I think that many of you should love this, are these short-lived zero-knowledge proofs and signatures. So The idea is, well, I'm not going to talk about the zero knowledge, but about signatures. So I can create a signature that is going to be valid, and like unforgeable only up to time t. After time t, an adversary can forge for free, the signatures. What it means is that, you're communicating with someone, and then, for this prescribed time bound, that you're communicating with that person, but after that time, if someone would go to judge and say, look, I have your signature on a message that says, rebel or, like obey or whatever. So then the judge has a problem because after time t, the signature of the original user, of the authenticated user and an adversary is indistinguishable. This is a very cool thing, right? You have deniability after time t for free. It's not something that you might want to have for your transaction ledger, right? That you can forge, but in this context, like deniable messaging, or when you want to invalidate email leaks after some time, or some applications to e-voting, it's very exciting. And yeah, given the time, I will skip this. So what we did eventually is we use this proof of exponentiation to speed up the search for the largest primes. If you want to hear about this, I would love to tell you about it, over coffee or beer later. So come to me. But yeah, so good. So what is the future? So the future is up to you and me and people that might be interested in this. So more cool applications. There are these VDFs. I mentioned some applications, right? What do you build out of these? And we have these things are very practically efficient. You get them. There is code. I think that the Chia network had in production some VDFs actually of the Veselovsky. So you can just build with this. So do build and let the the space know what cool stuff you build. And to me, where is this sequential hardness? Is it something very rare? How do we get them? I want more candidates, right? So that I know that we actually are using secure primitives, post-quantum candidates, right? I don't know if there's ever going to be a general quantum computer, but people seem to be worried about it. So we might as well look for post-quantum candidates and optimal implementations, right? If you're a algorithms hardware person, this is a question that you should love, right? How do you do the function that you iterate in the best way on the planet, right? So that we can time these VDFs correctly, right? And yeah, so that's it. If you want to look into it, just pointer, there is this amazing website, vdfresearch.org, that collects pretty much all the resources that are there. So, that is a great place to start. They have a lot of pointers to YouTube videos. And I just want to shout out to Martin Matejka and people from Firefish. So they kind of connected me with the HCPP, and I'm very happy that I had the chance to tell you about what I've been working on, what I think is cool. And I always love talking to practitioners. So, if you have some interesting problem for a theoretical cryptographer, I would love to hear about it and collaborate on that. So